topic is basically always been widely talked about and a highly one of interest. There are classes given on this topic that are basically a week long to 4.5 days to 5 days. And even then, you're still not an expert in sample handling when you take those classes. So today will be the 50,000 overview, but just enough so that you know what to ask about. We're going to do a quick review of design considerations. Then we'll go into the basic components. We'll spend a little bit time on probe location. Basically, that's critical because the GC works like a junk in, junk out. The probe is your first part of the sample handling system. If you get it wrong there, it's not going to make up for it later down the line. We'll spend a little bit of time on lag time delays. Obviously, the big focus has always been sample lag time, but there's also other types of time delays in your system. And then finally, importance of phase diagrams. When you come to us or even one of our competitors, the first thing we'll ask you about is your composition of what's flowing through your pipe, as well as your temperature and your pressure. Because it's important for us to know not only what you're looking to analyze, but where you are in your phase diagram. So just a real quick survey. What percentage of GC problems are the result of a poor sample handling system or basically a contaminated handle? Oh, wrong one. Okay, you guys don't see that. Let me push the audience. Do you see it now? Yes, a little slow. So we'll give you about 30 seconds to fill this out. If you haven't attended any webinars or seminars on sample handling system, or even just on GCs, you probably will know the answer. Okay, I'm just going to quickly go. Are you seeing it? All right, so we got a smart audience here for not attending any past webinars. You are correct. 80% is the number that you will generally hear people talk about. So you can understand why it's important to us, because when something goes wrong, of course, it makes our GCs the prime suspect. And a lot of times it's actually not the GC itself. It is the sample handling system. And it's just because it's a very complex and there's many integral parts. So if you get one part wrong, the rest of the system can't make up for it. So what exactly purpose of a sample handling system? You seeing it? Okay. It has 5 functions. 1, it needs to take a representative sample. Basically, whatever's flowing in the pipe is what you need to be able to pull out of that pipe and send to the GC. The GC gives very accurate results. It will analyze what you gave it. If you do not give what's flowing through your pipe, the GC will not know that. It will give a very accurate answer of what you gave it. So if it's not what's in the pipe, you're not going to get an analysis of what you're looking for. 2, especially for gas or vapors, reduce and control the pressure of the sample. The lines can be running anywhere from a few hundred psi to a few thousand psi. And the sample handling, or the GC inlet sample, is generally between 10 and 30 psi. So that's a significant drop in pressure that needs to happen. And we need to be careful when we drop that pressure that we pay attention to the Joule-Thomson effect. And that is basically means that for every 100 psi drop in pressure, it's a 7-degree drop in temperature. And so when we do initial phase diagrams, you may be looking at a nice good area on the, in the vapor phase. Dropping that pressure can result in a drop in temperature, and you can actually go into a 2-phase situation. So it becomes very critical when we're managing the pressure in the sample handling system. It's also important when you have liquids, because a lot of times you may want to maintain that pressure or even increase the pressure to avoid bubbles forming in the liquid. To remove solids, you will see that it's very critical. Every sample system or any stuff flowing through the pipe picks up gunk. And the GC doesn't really handle that well, so we need to remove that before they get to the GC. So we often recommend various different types of filters. Also remove any free liquids. Again, the GC operates on clean, dry gas. Anything that's not that will be a problem for the GC and could be a very expensive repair. Another issue with liquids is that the GC, in most cases, will vaporize that liquid. But what can happen is maybe a liquid was 0.1% in your sample, but when it gets to the GC, when it vaporizes, it's going to go to like 600%. So obviously that will change the concentration in your sample. It would no longer be a representative of what was flowing in your pipe. So it's very important that we remove the free liquids. If you're able to do the above 4 items, makes maintaining the composition of the sample much easier, but you still do have to be careful about hydrocarbon dropout when you're changing the pressure, which can affect the temperature. Okay. So as we mentioned, 80% of the problems are caused with the sample handling system, but if we get that right, then the GC will operate as designed, operate reliably, and require minimal maintenance. And that's important for both parties. One, we love it because we get less questions and problems and phone calls, but more importantly, on the side of the customer, it's a less issue in terms of cost and time and basically analysis. You're getting what you paid for, and so you're getting the accurate answers in the timely manner that you need them. Okay, we're going to move on to design considerations. Any questions at this point? Looks like no, so it looks like we're going to go forward. Things to consider. One thing that always comes up is compatibility. Whether you're running a liquid or a gas, there's a lot of components in the sample handling system. Will there be any interaction? So the common one we always see is H2S. You know, we recommend normally 316 stainless steel, but if you have H2S of certain concentrations or greater, then we will ask to be silica-coated tubing that we will offer instead. Pressure limits. We've kind of talked about this before, but you could be running at several hundred PSI in your pipe, and the GC can only withstand 10 to 30 PSI at sample injection. So we need to have a way to make sure that you have a way to get that pressure down to be compatible. Sample transportation configuration. We kind of discussed a little bit this concept when we did the installation considerations, but where is your GC going to be put versus where the probe or the sample point is going to be at? You know, we always tell people get the GC as closest to the probe as possible, but we understand that's not always something that can take place. Another item is flow rate. How fast is your liquid or your gas flowing through the system? And when I say system, I mean the sample handling system. That has an effect on the lag time. It also has an effect possibly on contamination. Tubing diameter. How big is your tube or how small? You always hear us talk about getting the smallest tubing possible. Generally for gas samples, it's been 1/4 inch. For gas, it's about 3/8. I'm sorry, for liquids, it's about 3/8. And then, as I kind of mentioned before, when you come into us, what's your sample at the source of the extraction point? We need to understand the phase. Is it a liquid? Is it a gas? Or is it possibly two-phase? Sampling conditions. What's the temperature? What's the pressure? What's flowing through your pipe? What possible contaminants? How is everything located? Okay. So there's a couple best practices that we're just going to briefly go over. One of them is eliminate dead space and volume. As you can understand, if you have more volume or space to fill, it's going to take longer to get a response, longer for your sample to get to the GC. Also, if you do have these dead spaces, it's possible, whether it's a liquid or a gas, to get into them. And then when you switch samples, you can actually do some contamination because now you have to find a way to get that old gas out of there or to purge it. And many times you can't. So you do want to, the best practice is to eliminate them as much as possible. Minimize the volume of the sample within the system. So it's, again, very similar concept. As you have pushing the thing through, the more volume you have, the longer it's going to take to get that all the way through the system. So if you can minimize that, you can shorten the response time. Then it's to minimize the internal surface area. So if you think about it, you have this gas going through. If you have a larger surface area, it's a possible absorption or having an interaction between that area as well as your sample. So if you can minimize that area, again, we always recommend the smallest tubing possible. You reduce those effects. we minimize the operating pressure in gas systems. Again, if you reduce the pressure, you reduce the volume. You reduce the volume, reduce the lag time, which improves the response factor. Also, you have a less likely, if you do have any dead space or anything, have the risk of absorption. I will point out, with liquid systems, you don't want to minimize the pressure. Liquid is actually, you want to maintain the pressure or possibly even increase. So minimizing reflux just for gas sampling systems. Minimize flow. So this one's a bit touchy because you'll hear us also tell you maximize flow. So it's really one of those situations that we call it quasi-dependent. So when we say minimize flow, it's really also most associated with getting at the probe. If the sample velocity into the probe is higher than what's flowing in the pipe, it acts like a vacuum and it sucks up the contaminants into the probe. If you do that, you end up increasing the filter life. You know, so the filters will catch it, but you're going to huge maintenance. Also, you flow, you worry about the pressure drop. So those things to consider. On the converse side, if you go too slow, one, and obviously you're going to increase your lag time because we'll get to that slide, but you'll see it's the denominator. So if you decrease that, you increase sample lag time. But the other problem too is if you have liquids, it's impossible to get particle dropout or solids forming. So when we say minimize, it really should be optimized. It'd probably be the best word. Okay.
Okay, hi everybody, it's Shane here. I just got a couple of questions that were asked through the Q&A interface, and they relate to the H2S, the coating that we use, the Silco coating for the stainless steel, well, the Silco-coated tubing that we use for H2S. And just to clarify, we use the Silco-coated tubing when it's a very low concentration of H2S and we're trying to measure it, because the issue with H2S is it's a very sticky compound. And so when you're trying to measure in the ppm levels, what can happen is that some of that H2S will stick to stainless tubing and stainless components, and so it doesn't make it to the GC. And so what ends up happening is that it becomes a H2S bank. And so if you're using just stainless tubing and you're measuring ppm level H2S, then high levels of H2S will stick to the edges, and so you'll get a lower reading. But then when the H2S reading goes down, some of that H2S that's stuck to the tubing will actually come back into the gas, and so you'll get a higher reading. And so the point here is if you're not using a coated tubing for low H2S measurements, then the H2S that reaches the GC won't be accurate, won't be the same as what's inside the pipeline. And so when we use Silco-coated steel is when we're measuring in the ppm or parts per billion levels of H2S, and it's to avoid the stickiness of H2S. So we use the coated tubing when we're trying to measure parts per billion or parts per million levels of H2S. Now, when you're up to 1, 2, 3% of H2S, we don't really need that coated steel because there's just so much of the H2S that the stickiness factor doesn't really come into the accuracy. But when we're looking at 10, 15, up to 100, even maybe 200 ppm of H2S, and we're measuring that H2S, that's when we're going to use the coated tubing. So just to clarify those two questions that were asked about the H2S, and hopefully that answers your questions.
Okay. And then we'll go back to, and we'll go on to components. So there's a wide variety of components used in a sample handling system. Probably the first one we start with is the probe. That's the one that takes basically what's flowing in your stream or in your pipe into the sample. There is a multitude of probes out there. We don't manufacture probes here. We obviously do a buy resell. We work with several probe manufacturers out in the area. But there's a couple considerations, and we'll talk about a little bit later. But you can get a standard probe, a direct drive probe, probe with a heated regulator, probes with membranes. So there's a whole bunch of options out there to pick, and it really does depend on the source conditions, your temperature, pressure, and the contaminations that are in your system. The next one is filters. We highly recommend filters. We recommend them on the probe. We recommend them on the sample conditioning plate. This is just a photo of a few of them here. We have a membrane filter. We have a Spatialock 2-micron filter that we put on all our sample handling systems. So it is important, again, it was one of the 5 principles of what the sample handling system must do, and that is to remove contaminants, both liquid and solid. So a filter is absolutely critical. The next item I'm showing is a regulator. Again, especially for gas systems, but obviously also critical for liquids, we need to get, for gas, the pressure down from a few hundred psi to the 10 to 30 going into the GC. You'll need a regulator to do that. Again, there's a multitude out there, so it's up to what regulators that you have a personal preference for. Talk to suppliers. If you come into us and we're designing the system for you, we will make the recommendation. The next item we'll see on sample handling systems is valves. And these can be isolations or shut-off valves, so that helps you with maintenance. It helps you with avoiding back pressures as well in certain cases. One thing we do mention here is make sure the orifice is large. The reason is that if you have the tubing going in and then the orifice of the valve is smaller, you will create a pressure drop, which is possible to then cause fallout. So we like to have that orifice as large as possible going through there. The next item is tubing. So in most cases, you got to get from the probe to the GC. You're going to have tubing. You heard Shane mention 3/16 stainless steel is our recommendation. Again, 1/4 inch most often for gas, 3/8 inch for liquids. A little note here, and that's just more for contaminations, that if you're going from the probe to the GC, it's nice if you kind of have it tilting upwards. That way the contaminants roll backwards, and kind of help gravity help you do the work. So those are the most common ones, but they're not the only ones that you will actually find on a GC. So depending on where you are, depending on your composition, you may need a heating element. So a lot of C6 plus applications, C9, depending really where you are, which is most of the U.S. anyway, you're going to have a heating system. You're going to have heat trace. You may, when we sell our enclosures, we have a heater in there as well. It's really to keep, keeping a good location on the phase diagram. So that's, you may have a heating element, a sample pump. If you don't have enough pressure from your sample point to the GC to get there, maybe you're several hundred feet in tubing length, you may need a pump to be able to get enough pressure to get the sample to the GC. There's also sample cylinders. Obviously, most of our GCs are connected directly online using tubing. However, there's a possibility of grab samples. There's a multitude of cylinders out there. Again, we don't make this product ourselves. You can talk to a vendor. You can come into us if you're interested in doing some grab samples, and we can make some recommendations for you. Vaporizer. So we've probably heard us already mention we need clean, dry gas into the GC. As some of you may know, we will work with liquid systems. Our reps work with liquid systems. Well, how do you go from a liquid to a gas? Well, you need a vaporizer. And there's different types out in the market. There's special ones for like LNG applications. But this is the thing that basically converts a liquid to a gas. And there's a couple concepts that you have to think about when you do that. You do need to worry about the amount of sample going into the vaporizer. What could happen is if you have too much volume going in, it all will not turn into a vapor. So you'll have basically a mixture of liquid and a vapor. Also, if you done correctly, it will fractionate, and therefore you won't get your sample going onto the G as a complete sample, but basically out in components. So you need to watch that. And then flow controls all the little miscellaneous giblets, I'd almost call them, that you have on your system. These are your rotometers, these are your double block and bleeds, your ARVs. There's a multitude of ones out there, and you'll see when we show some examples of sampling handling systems later, you'll see a couple of those. This is just a very straightforward, if anybody's taken any of our webinars or classes in the past that we show, But it just kind of shows the most common things. We start with a probe. We will also have a membrane or primary filter to basically clean off any liquids. Any solids will drop off. You'll then go up to the probe head where you'll have a regulator in most cases, again, to get that pressure down. Depending on what you're analyzing and depending on your ambient conditions, it may be a heated probe regulator. We then recommend after that that you have an isolation valve. It's also likely you have an isolation valve on the probe as well, but this enables you to do maintenance if you have to disconnect the tubing. In this particular case, we're just showing straight tubing, and again, you could have this heat trace depending on your ambient conditions as well as what your sample consists of. Finally, we have what we call is the sample handling plate. This is your last line of defense before the sample goes into the GC. So again, we recommend you have a membrane filter as well as a micron filter there to eliminate any liquids, free liquids, as well as eliminate any contaminants, even in the principles of the 5 things that the sample handling system must do. Okay. If there's no additional questions, we'll go on to probe location. Okay. So taking the same screenshot from the last slide, this is a vapor sample. It's in the pipe that's horizontal. This is actually pretty much the ideal condition for a vapor. We always tell you to be on center, 1/3. And so you want the probe basically 1/3 of the way down in that center section. And the reason for that is if you get too close to the pipe wall, you pick up the contamination of the schmooze that's there. So if you're right in the center, it's a good spot. We do say no longer than 10 inches. It's not because we think you're going to hit the bottom of the pipe or it gets contaminant. It's basically you now become this long, thin pole hanging in a pipeline, and if a gust of gas comes through, you could actually snap the probe and it goes downstream, not making the people who are downstream of you very happy. So we do say between 2 and 10, obviously depending on the pipe diameter. If you don't have a choice and your pipe is vertical, you do have 2 options. You can either put it horizontal or at a 45-degree angle. In this particular case, your probe, basically whether it's a square probe, it has a slant, whether it's a little, different types of probes are out there, becomes much more critical based on the characteristics versus when it would say it was a horizontal pipe with a little bit more flexibility. This one you do need to understand what your composition is, what your flow, what your directional flow is. You can do a 45-degree angle if the flow is up, but in this case I have a squared probe, so it only is recommended for flow that's down. If you were to have flow up, or preferably that you would then have a slant or cut into the probe surface to help avoid contamination. If you have liquid and you're flowing through a horizontal pipe, it's kind of like the opposite of gas. You're going to want this basically on the side of the pipe, close with the probe tip going close to the center. Again, also though, in the third, you don't want too close to the top of the pipe because there could be vapor up there, and you don't want it too close to the bottom of the pipe, again, for contamination issues. So that's kind of that. And then for probe location, if you have a vertical pipe, that's actually, if you're flowing upstream, it's one of the best locations is to have a vertical pipe for liquid flow. That said, if you do have liquid flow is downward in a vertical pipe, it's really not an ideal location for a probe because you don't know that whole pipe is going to be filled with the liquid. It could actually be multiple phases in their 2 phases. So keep that in mind. And as we put on the bottom of all these slides, the best thing you can do is have the probe as close to the analyzer as possible. That eliminates a lot of issues. We know that's not always keepable, but just try to keep that in mind if you're designing a new system. So we talked about where to put a probe. The other question is where not to put a probe. And one of the biggest issues is not near any turbulence. As you can imagine, or restriction in path, because that will cause all the contaminants that are on that pipe wall to get all stirred up and mix into what's flowing in the pipe. So you really want to stay away from that. And so depending on what you read, what the requirements is, whether it's EPA, some countries have their own requirements as well, but general rule of thumb is between 2 and 5 pipe diameters away from anything that would cause a turbulence in the pipe. So I'll kind of just show it in this example. Another thing to keep in mind is if you're designing this and you have the opportunity is keeping the probe in a place that's easy to reach. These are not our photos. I did take them just to give out credit from a paper that Amatec had did, showing some less than perfect places to put a probe. You have to understand if the probe is not in an easy to reach location, maintenance is probably not going to be done. And if you're doing any grab samples from there, it's even more difficult. So if there's not any questions, we will go on to timelines. Wow, okay. So there are several causes of various different lags within a system. One of them is the people sometimes overlook is the process delays. And so what could happen is it's more probably you'd see it more in a chemical application than a C6+ pipeline. But you have your probe at the end of, if you have that probe several yards away from the end of your process that you're trying to measure, it's going to take time for that fluid or whatever coming from that process to hit the probe. And so that's going to be a delay. There's nothing else further downstream, or you don't make up time. Two, if it's a low flow liquid, say, it could even take longer. So keep that in mind of what you want to measure and how that dictates where you're going to put the probe. And also understanding that sometimes there is a trade-off where coming out of a process, maybe it's very hot, and so you can't quite put a probe there. You do have to put it further downstream, but just understand that it's going to add analysis time into your system. And then there's the measurement time for delay. And that's basically how long does it take the GC to do an analysis. On C6+, we range anywhere from 2 to 4 minutes, but obviously on some of our chemical applications, they're 10 to 30 minutes. So you do need to keep that in consideration if you're making a process change, when you're going to find out the effects of that change. And then the one people tend to focus a lot on is the sample transportation delays. Again, we'll show on the next screen there's a formula, but again, how far you are from the probe to the GC, whether you're flowing a gas or a liquid, how your flow rate is it slow, is it fast, comes in play, as well as we talk about high pressure, which you don't want for gas lines. You want to keep the pressure low. High pressure means more volume. More volume takes you longer to get from the probe to the GC. There's not any questions. We'll go continue. You see the equation here, length times cross-sectional area divided by flow rate. So this kind of goes back to what we talked about. Keep your probe as close to the GC as possible because that affects the length. We talked about really having the smallest internal volume. That's the cross-sectional area, not only for absorption area, but again, it affects the amount of volume of the sample that you're having going through there. And then the flow rate. We'll see people say, well, let's run it as fast as I can then. And, when we talked about the contamination issue, but sometimes, getting your sample from the probe to the GC quickly doesn't always do you a lot of good if you haven't fixed the other delays in the system in terms of where the probe's located for the process, as well as what your analyzed time is. If you're looking for an answer in 2 minutes after a change in the process, but your analysis time is just the GC is 10 minutes, it really doesn't make a difference how long it takes the sample to get to the GC. But the general rule of thumb is your lag time should be half of what your analyzed time is. So you always have what we call here, and we put in parentheses, fresh sample to the GC. If there's no questions, we will move on to phase diagrams. Okay. So we have basically just kind of a chart here, reminding you again, clean, dry, gas, what we require into the GC. And while we do liquids as well, there's different things if you look on the chart below, which is more looking at where the hydrocarbon dew points are. But we broke it out into 5 categories: cryogenic, like LNGs, light gases, heavy gases, light liquids, and heavy liquids. For this presentation, we are not going to talk about LNG. It's a special case, and we could literally just spend hours talking about LNG and its sample handling system. So we're just going to focus on the other remaining 4, light gases, heavy gases, light liquids, and heavy liquids. So here you'll see is a classic phase diagram. On the horizontal, it's temperature. On the vertical, it's pressure. On the left side is your liquid phase. On the right side, it's a vapor phase. Between those, underneath the curve, is the 2-phase area. And actually, one reason we do ask you what your temperature, your pressure, and your composition is that you want to be analyzed is because we need to know if you're in that 2-phase area. If you are in the 2-phase, we won't offer, we'll no-bid the project because we cannot accurately measure if it's in 2-phase. If it's a liquid or a vapor, we have a good chance that we can help you. Some other points on the curve, you'll see the bubble point curve, and that's the temperature at a given pressure where the first bubbles of vapor start to form. So you never want to be anywhere on the curve, to be honest with you. So these things are important to keep in mind. On the other side of the phase diagram is the dew point curve, and that's the highest temperature at which a vapor will form, or it's the highest temperature at which the vapor will condense into a liquid. There's 2 other points on the curve. You'll see the Cricondenbar, and that's the maximum pressure by which no gas can form regardless of the temperature. And the Cricondenbar is the maximum temperature by which liquid cannot be formed regardless of pressure. So let me say this again in case I think I sound like I mixed them up. Cricondenbar is the maximum pressure by which no gas can be formed regardless of temperature, and the Cricondenbar is the maximum temperature above which a liquid cannot be formed regardless of pressure. And so that kind of helps us determine when you give us your composition and your pressure and your temperature, where you're at, and things that we need to keep into consideration. Now, for simplicity, for the 4 types of light gases, heavy gases, light liquids, heavy liquids, I've kept the same curve. In real life, obviously, they would all be different. So here's an example of a light gas. If you're in this particular situation, it's actually one of the easiest sample systems to design for. In this particular case, you're vapor, you're not particularly close to the curve, and so you can just strictly do pressure reduction and not have to worry about hydrocarbon dropout. So here's a quick example of our type of sample handling system that you could have. You'll notice that it, again, we'll push this point a few times, but it has a 2-micron-inch filter. It also has a membrane filter. Again, keeping with the 5 principles of sample handling system: remove contaminants, remove free liquids. There's also a flow indicator as well on the bypass. And we do recommend bypass. One, it helps keep the liquid membrane filter, it keeps a differential pressure, and it's constantly sweeping the free liquids out. So that's good. And then in the flow diagram, it just kind of, in this particular case, the flow indicator, it just gives you an idea of what you're flowing, and you can make an adjustment. So we always tell people to try to keep it somewhere in the middle range, and that's something you can help determine with your lag time as well. Here's an example that possibly if you have a heavy gas, you can see at the sample point, you're somewhat closer to the curve now, so you do have to have some care. You just can't just reduce the pressure. You don't want to get too close or basically go across that line and enter into the 2-phase zone. So this time you would reduce the pressure, but you would also be maintaining the temperature, if not slightly increasing it, so that making sure, again, you stay away from the phase boundary going into the 2-phase area. Here's another heavy gas example. This one, you are really close to the phase curve, the 2-phase zone area. You're basically right about the Cricondenbar. You're basically near the hydrocarbon dew point. And so at that point, you're definitely going to you don't want to take the risk of reducing pressure right away. You want to get the temperature up. You want to get away from that curve. Once you've done that, then you can safely start reducing the pressure. So another heavy gas example is this time you have a lot of pressure and you're also close to the curve. So you will have to do this one in stages. A lot of times it's either a 2-stage regulator or a 4-stage regulator. Again, you're going to want to apply temperature first before you start reducing pressure. You need to get away from the curve. Again, you're going to do this in stages because you're probably going from maybe 1,000 psi trying to get down to about 30 psi. If you would just do a little bit of a temperature increase and then quickly drop the pressure, you could still go pass through the curve and go to the 2-phase zone. So you're going to do this in steps. You're going to apply pressure, apply temperature, reduce pressure, apply temperature, reduce pressure. So I don't know if you guys comes out clearly in the animation on the slide or not. But here's an example of a stream that we have here, and this is actually a single stream with a grab sample. You also notice that we have to have a pump as well. Again, for the in this particular example, the pressure was not enough in the sample to get it through the system, so we do have a pump. You'll also notice that the tubing looks a little different. Again, this particular sample in this case had H2S in it that we were measuring. So Shane previously talked about the silica-coated 3/16 tubing. This is what it would look like. It's kind of that orangey type of copper look in there. And talking about orangey copper look, you'll also notice we have heat trace. So this is an example where we had a heavy gas come through. We make sure that as we are going through the system that we do not lose our temperature. In fact, we maintain it. So we do have heat trace in this particular sample conditioning box. And if you look at the drawing on the left-hand side, you can actually see where the heat trace boot would come in with the sample. Because we do have a grab sample option as well, you do see a pressure regulator that you would make adjustments to that. And we do have in the addendum that I attached as one of the resources talks about how you would purge that regulator to ensure that you got all the air out of the system and any contaminant before it went on to the GC. But because you have that option, there's a double block and bleed. So one of the flow control products we had talked about, it's basically on the right-hand side in the center of the view. And then above that, you will see some ARVs as well as some flow control, or actually really flow monitors, flow indicators. And the reason they have the ARVs is, again, it has H2S, so they are likely venting to flare versus venting to atmosphere. And our sample loops in our GC need to vent to atmosphere to equalize, to have a consistent sample size. And so an ARV allows us to equalize our sample loop to atmosphere without actually venting the sample to the atmosphere. And this is just a little bit more indication of, if you were looking at it, the various components that you would need in the sample handling. And this is really just the conditioning plate. So there is the whole probe and tubing and everything beyond this, and pressure regulator that you don't see that would be in addition to the sampling plate. This is just really the last stage before it hits the GC. So you can see they can be pretty complex. In this example now, we'll move on to the liquid. And this one's a light one. So this one's actually a light liquid at very high pressure. And so in this particular case, you would vaporize at the sample point, and then maintaining and increasing temperature and maintaining that until you got well past the Cricondenbar, and then you can start decreasing the pressure. So in this particular case, because it was so high, that it made more sense to actually vaporize it at the sample point versus waiting to like the sample conditioning plate. And from our perspective, because it was already vaporized back near the probe area, the sample handling plate would actually look very similar to what it looked like for a light, and in fact it still says light gas on it. I didn't change it to say light vapor. So it really would be the same plate from our perspective. It would be different, obviously, at the probe, how you did things, but at the end part, right before the GC, it would be the same sample handling system as a light gas. Here's an example more if you had a heavy liquid. So in this particular case, you're pretty stable at where you're at in terms of the temperature and the pressure. So at this point, it's easier for us to maintain the temperature and the pressure. In fact, pressure becomes critical. We want to maintain that, ensure that we don't run into the issue where we'll have bubbles forming into the liquid. But we will vaporize this one. We will keep it in the liquid form till right before we get to the GC. And that's why the line's kind of dotted here. You're going to basically maintain your conditions, and then right before the GC, you're going to vaporize it. And so if you look at this particular liquid sample handling system, you'll see you're coming in. You can see the pipe, if you look at it, it's definitely bigger than you've seen in the previous versions. This is probably more close to the 3/8. You're coming in with a flow monitor, as well as, we call these a tornado filters, but basically it's basically a liquid contamination filter that sweeps clean. And you'll probably be squint really, really hard, and you can probably see it more when I get to the diagram. But as you go into the sample conditioning plate, and it's a heated plate, as you can see in the right-hand picture, we decrease the tubing size. Again, you do not want to have a significant time go into your vaporizer. When you vaporize a liquid, you can literally go up to 600 times the initial volume. So you need to be very careful about overloading the vaporizer. You want to make sure you don't do that, again, because you can cause fractionation, or you can cause basically a two-phase situation where only half the liquid will vaporize, the other half will stay as a liquid and go onto the GC that way. If we look closely too, again, we have this is actually a two-stream coming in. So we have a double block and bleed. We also have an ARV and a flow control. If you look, kind of squint, center, so it's the right photo. In the center, you'll see a coil. That's a vaporizing coil, and that's for the liquid calibration coming in. So you'll have to have that vaporized coming in, and a little bit past the vaporizer, you'll see that again we have more filtering. This would be the schematic of what that sample conditioning plant looks like. It's a little harder to see, a little bit more components on this system as well. Heat trace, keep the temperature. Again, we have two streams, so we have solenoid switching back and forth, double block and bleed. And as I mentioned, you'll see the vaporizer coil for the liquid calibration gas coming in, and then the vaporizer for the liquid sample. All right. So if anybody has any questions that they haven't gotten in yet, again, the Q&A box is at the end or underneath the slides. There is no voice on this email, and why it looks like we have some, so Shane's getting up and ready to answer the questions. I just want to show you that we have put together a schedule for 2017 for our on-site training classes. So definitely go to My Connect or all up there to see what you would like to take for next year. It looks a little empty on the calendar. We have some internal training done, and we can always do a custom training class for you as well. Again, because we've hidden the links, I do recommend that you download this presentation. If you have us in presentation mode, I do have direct hyperlinks to all the previous webinars so that you can get there anytime. These will be up there. We're not taking them down. So just be, we don't put any restrictions on these. If you're ABB, you may not be able to see them, but everybody else should be able to. And then while we start answering some questions, I put together a list of possible ideas for webinars for next year based on some questions we get. But if you don't see what you want to focus on, definitely send us an email, analyzers@emerson.com. We want to make this for you. This isn't for us. So whatever you guys want to talk about, we'll get it scheduled for next year. And so let's review the questions.
Okay, hi everyone, it's Shane here again. There was two questions that were asked. One of them was, is there a recommendation for how far away from the phase curve you want to stay as far as pressure and temperature to maintain the phase of a sample to keep it a vapor? That's a good question, and actually that brings up an issue that we see a lot. It's people draw up the phase curve and they say, hey, the hydrocarbon dew point is going to be at, say, 50 degrees, and the temperature's never going to get to lower than 55 degrees Fahrenheit. And that's, theoretically, that would be okay, but the problem is one of the first things you do when you take a sample out of a pipeline or a process is you lower the pressure. And when you lower the pressure, you're going to have, you're going to lower the temperature as well, thanks to the Joule-Thomson effect. So you don't want to be exactly next to the curve. The general rule of thumb and the recommendation that's in the API 14.1 standard is to keep the sample at least 30 degrees Fahrenheit above the hydrocarbon dew point. That means that really when you're looking at a sample that could possibly be near its hydrocarbon dew point, you should always heat it immediately as soon as you take it out. Now, the question is what's the hydrocarbon dew point of the sample? And to be honest, that's why you often have a gas chromatograph or some other analyzer, is to calculate what the hydrocarbon dew point is. So you don't know what the hydrocarbon dew point is. But I can tell you that the highest possible hydrocarbon dew point is always going to be the process temperature. Because if the hydrocarbon dew point for that mixture is higher than the process temperature, then the heavies will drop out, it'll go two-phase, and the gas phase, which is what you're going to be sampling, the hydrocarbon dew point is going to be exactly the process temperature. So the highest hydrocarbon dew point for a sample can be, for a vapor sample, for a gas sample, is the pipeline temperature. So to maintain that 30 degrees above the hydrocarbon dew point, a good rule of thumb is to be 30 degrees above the process temperature. So if you've got a sample that may go two-phase or may be close to being a two-phase or near the hydrocarbon dew point, then you should heat the sample above the process temperature immediately as soon as you take it out. And you want to do it either at the point of pressure regulation or before the point of pressure regulation, so that when you do that pressure drop, you're going to decrease the temperature of the sample and you're going to thus maybe go close to the hydrocarbon dew point. So the rule of thumb there, according to API 14.1, is 30 degrees Fahrenheit above the hydrocarbon dew point. The maximum hydrocarbon dew point will be the process temperature, so you should heat it 30 degrees above the process temperature. Now, another issue, that brings up another issue which actually wasn't brought up in questions, but I like talking, so I'll bring it up. Often we will get these compositions come into the GC factory, and this is what the composition is going to be, and so we work out the phase diagram, and then we get it to site, and then all of a sudden we find out we have a whole lot of problems with the sample system, because the composition that was given to us was the ideal composition. It was the nominal composition, the composition that they think it will be. Now, that would be wonderful if everything in life worked out to be ideal, but it never does. So when you're designing a sample system as well, you need to design not for the normal condition, not for the standard condition. You should be designing for the worst possible condition, because really there's two things there. When you have the worst possible condition, when you have maybe the separators are not working anymore, or something's happened in the process, and so you're now getting a heavier sample than what you expect in a vapor, then you need to plan for that, because you don't want that contamination getting into the GC. For two reasons. One, it could damage the GC. So if you've got a whole lot of carbon fines, or maybe compressor oil or something like that suddenly hits the sample, then you don't want that going into the GC. So you need to design your sample system to account for those critical failures that may happen upstream. And also, we need to be able to measure when you've got bad process conditions, because the time that someone is looking at that sample and looking at that composition is often when the plant is out of control or when the process is out of control. And so you want accurate results when the process is out of control. So when you're designing a sample system, don't design the sample system for that ideal condition that, let's be honest, never actually happens. You need to design for the worst conditions, so that when things are bad, when things are not working the way they should be, your sample system is working correctly and your GC is giving you results that you can act on and actually use. So that's just another recommendation that I give. Now, I've got another question to come up. Oh, no, just a thank you. So we'll leave it open for another 2 or 3 minutes, and if you've got any questions, please write them into the chat interface, and also please answer the poll and give us an idea of what we can do in the future. Okay, so we're waiting for questions.
So I'll do the politically correct thing, and if you notice, some of the photos we've taken are from some of our suppliers. To just give credit, we do use Space Block, we do use Genie probes and filters, so A+ Corporation as well. Yep. Just because I didn't get licensed to use those photos, so thank you for allowing us anyway without your permission.
Forgiveness, and also our friends at Mustang Sampling as well. I think we've called out to almost everyone, and also Welker. We use Welker a lot as well, and they're all great suppliers of sample handling systems, and I think that'll get us out of legal trouble there, Bonnie.
Okay. If not anything else, then we will end it here. Again, this is always available for replay. The hard copies of the presentations can be found on the website as well. So great. Have a good day, guys. See you in 2017.
Thank you. Bye-bye.